me, Sarah. And it's great to be with you guys. I want you to know I have a longer version of this than what I'm going to give tonight that I can share with y'all. If you connect with me on LinkedIn, just message me on LinkedIn after we connect and I'll send you the longer version. On the side, I didn't think of this at first, Sarah, but I've been studying reinforced learning and loving it. I took the extra time to program my own environment in Visual Python, if you guys have ever heard of that. And then I got to a certain point where I was getting okay with reinforced learning, and I switched to transformers. And luckily, I started a learning group on LinkedIn, and it attracted a really heavyweight. If you guys don't know Dennis Rothman, Dennis with one N, highly encourage y'all to connect with him and follow his posts about, I know too much. He's going to be releasing something very helpful about learning transformers here in the near future. So if you guys have taken an interest in that and seen the power of them, I encourage it. But by comparison, this presentation, which I usually give with a couple of international friends, is very basic, but a high-level overview of the supervised machine learning process, making a pipeline, and hopefully eventually getting it to automation. And we've been pleasantly surprised. We presented this as something that is a great introduction to new people, but also for very experienced people who maybe never heard it, seen it put this way. They found it valuable too. So I thought I'd share it in hopes that you guys found some value in it too. Let's see. And just the spirit of this is, I'll read this out loud. Sorry for reading. I've encountered many great mentors in many forms. One powerfully recurring principle taught by them: the greatest practitioners in any field take the time to master the basics. The basics are the foundation of any great art in life. Masters literally practice the basics tens of thousands of times. I am all for the latest cool tools and techniques. They will crumble as a house with a poor foundation if not built on good basics. And that's really the spirit of this presentation, is to look at the basics together, but in one big picture. And I warn people that are new to data science, if this looks something like walking into a commercial airline cockpit, then you're probably having the appropriate reaction. But after we get to the very end, I hope you'll see this and go, oh, okay, that's not so bad. And hopefully this next picture gives people relief. This is the basic pipeline. And I'm using a mind map layout, but which isn't the best way to do this, but we decided to do it for the newer people. And as you guys know, we start with features or inputs. And then from that, we use labels to train our models. But even if we get this whole process automated, which is possible, just like any machine in life, we still have to provide human oversight. And that's because, as we know, we're almost always working with samples of bigger data sets. And as the data grows and flows, we might need to alter our models, and we'll get into that too. Let's see. So I'm guessing most of you know this stuff, but this is just a quick overview for those that are new. Features is the term we normally use, but it's like inputs to our model. Our model's crap when we start. It predicts something. We get an error between that and our labels or our outputs, and that provides some training ability with objective functions. And it wasn't an intention to go into that here, but the main thing to remember, which I'm sure you guys know, all machine learning problems are math problems. Well, why do we say that? We'll get into that in a minute. So we have to deal with many things, and I'd say, you guys probably agree, 80% or more of what we do is just dealing with the features at these different levels. So missing values. I won't go into this in detail because of my time limit, but we're either going to delete records because of missing values, and sometimes we delete entire feature sets, or sometimes just records. Sometimes we have to do a little bit of both. But luckily, sometimes we can actually do modeling, predictive modeling within the feature set to fill those in. And it depends on the nature of the missing data. But I used to feel a little sheepish, honestly, when I would do this. And then I started seeing more and more posts of others confessing that they did it too. And then I realized, oh, it's actually a really standard practice. But depending on what you have, you can see these different types, and you just fill in with what makes most sense for the type of data you have. In the kind of work I've done in the past, most of my fill-in was with linear interpolation. And literally, you're just taking one of the features that has more missing data, and you're using the other features that are more data rich to build a predictive model to fill those in. That's one example of this. And then, of course, we have to clean and format. I feel like I do that most of the time when I'm getting a model ready. I'm not going to go into detail on this slide because of our time limits, but again, I think you'd all agree that we spend cleaning and collecting and formatting data is probably about 80% of our work. Of course, there can be other things, and this is a little mixed with the previous one. But then, to me, this is where it starts getting fun, and in my current role, I do a lot of this sort of thing where we have to encode text, because again, all machine learning problems are math problems, and math problems need numbers. So if we want to, there's three basic types of encoding. One is one-hot encoding. If I have red, blue, and green, and I want to one-hot encode it, I can really just do it for red and blue. And when I have those zeros, that implies there's green. In fact, we really don't want to fall into this dummy variable trap and use this one. That's the only thing to remember when you're working with one-hot encoding. But then there's ordinal. If we have something like a quality scale, for example, we just turn these into accordingly. We give them numerical grades instead of word grades or letter grades. But this is my favorite one, and I've found some huge benefits from just thinking about how can I take a corpus of documents and look at the total vocabulary. In my case, by the way, I love my current role, but I'm not doing what I would call natural language processing. I'm doing what I would call technical language processing. So I've got to deal with test agency names and their test numbers and units and numbers and terms. And that doesn't play well if you use the typical natural language processing tool. So even though I'm saying words, they would be tokens here. That could be pieces of units even, or ISO, or 1160 for the type of ISO. But this would represent the numerical indices for each of those tokens. And then for each document, it says the occurrence rate of that token. And once you get something like this, it's amazing how fast, with sparse matrices and in SciPy and other tools like that, that you could do a cosine similarity between this multi-dimensional space we have here now, and find, like if a new document came in and you wanted to find the document that it was closest to or an exact match to, now you can do that lightning fast. It was so exciting for me after trying many things to see that, oh, I can find the closest document match among 65,000 documents with a total of 20,000 tokens in under half a second, imperceptible to my users. So then we normalize, and I think you'll probably know this, but we're just trying to get all our features on a level playing field. And there's a real reason we want to do that. There's different types of scaling, of course. The one I bet we use most of the time is standard, but this is where you have to get to know your data very well. Oh, by the way, I forgot to mention, the first thing I like to do, and I'm guessing you guys like to do it, is when you're getting to know your features, when you're when you're getting friendly with the data, it's really important to look at your histograms on each feature just to see how they distribute. Then, to me, these really are part of formatting to me, in a way. I mean, normalization to me is just another form of getting the data in a great format for the purposes of modeling. But obviously, we want to get rid of features that would cause problems or don't give us any value in the model, and that's so that we can have good parsimony. And let's go through that. So what are the reasons why you'd want to reduce? Well, collinearity would be one. And that's when we realize, oh, treat your features like players on a sports team. It would be really counterproductive to have two of your talented players doing the same job. And we look at the features the same way. We're just trying to get rid of, we're trying to identify those features that are trying to do the same job, but keeping the one that can do that job the best. And we'll talk about that some more. But we can also look at correlation strength too. By the way, this is feature to feature when we look at collinearity, but it's saying that two features correlate strongly with one another. You don't want that, but however, you do want strong correlation between the features you're planning to keep and your labels or your outputs. And then one of the tools you can use to see how strong those collinear features are is PCA. The one that's got the highest eigenvalue of those that are collinear, that's the one you want to keep. And we'll go into some more. So I'm pretty sure you guys all know this, but this would be not collinear between two features like age and limit. And then this would be highly collinear. But again, what we're saying is not correlated here and correlated, and we're speaking about features. If this were a label and this were a feature, then we would like this, of course. And then some of the methods we use to look for correlation, well, there's Spearman's, I'm probably saying this wrong. I forget their names. There's a couple, maybe they'll come up on another slide. And then, but we can also loop the model through removing or adding certain features to see what happens to the performance of the model. And by the way, I'm about to tell y'all you should try many different models because we can never know in advance which model is going to work the best. But one thing I stress to people that I teach, you want to be very good at linear regression and logistic regression. And you always want to look at those when you're developing a machine learning pipeline because they can tell you the most through their model weights. But if we don't scale our features, we can't get that insight. So that's why it's so important to do scaling. That is, if you want to get the big insights you can get from linear and logistic regression. So we can loop through and see, oh, okay, when I remove that, what does it do to the model metrics, et cetera? And we'll go into that a little more later. Lasso is a way to just force the weights to zero for features that aren't important. And Ridge is another one. Again, I'm pretty sure most of you guys know this, but do reach out to me on LinkedIn if you want to know more. And then again, we want to use the model metrics at this point. We're looking at accuracy, how well the model generalizes, meaning it's not overfitting, and the parsimony, meaning we want the simplest model for the job that does the job well enough, but doesn't start to overfit. And so we can, it's this iterative process we can go through, but what I'm trying to drive to is we can even get all this stuff to a way we can automate it. And again, PCA to help us determine when we do have collinearity, which of those collinear features do we want to keep? Just indications of perfect positive and negative correlation and everything in between where we have no correlation in the middle. Again, correlation's a great thing when it's features to labels. It's a horrible thing when it's feature to feature. Okay. This is the point I was making just a moment ago. Some models are used in production. Some models are used for clarity. Sometimes the same model is used for both. And that's what I mean about linear regression. Again, I don't always use it in production, but I always try to look at it. Okay, and then finally, once we've, and I can imagine people might have different feelings on this. I personally prefer to reduce the features first and then start looking to see if I need to engineer any features. And I can imagine there's cases where you might do these hand in hand. But just the simplest example I could think of, if I've got features that are called X and I don't have any engineered features and I have labels that look like this curved group with a little bit of noise, this is what happens when I don't have an engineered feature. If I've got features X over here and I add one engineered feature X squared, then I can find a way that really reduces the error. And so that's just the simplest example I could imagine of an engineered feature. Now, even once we've looked at a bunch of potential engineered features, we're going to reduce out the ones that aren't giving us any value. A lot of times, if you're doing this manually, of course, you've looked at your histograms, you've looked at plots of each feature correlated to the label, you get a feel for what engineered features you need. But sometimes things get so stinking complicated that we turn to deep neural networks. And as most, well, in case you don't know, there's an advantage to deep neural networks. They can do your feature engineering automatically, but we still like to reduce features, in my opinion, as much as possible because the data needs are so massive for neural networks by comparison. So I'm still a big fan of doing as much manual, or as I'm hinting at, automated feature reduction before you pass in a neural network, because then you just get a more economical neural network. Okay, so that's all the features. Now we're starting to look at the labels, and just briefly, I got a confession to make. I think I bombed a technical interview really seriously, because never in my life had I seen anyone, or I probably had and forgot, engineer a label or engineer the labels. And they just basically put the labels on a log scale, and when they plopped that problem down in front of me in a tech interview, I just bombed it because I kept getting hung up on, but it's on a log scale, and I should have realized that was just to linearize it and simplify the feature engineering, and that's truly what they were. But one of my favorite friends is really good to emphasize to new data scientists, hey, you got to remain open, you got to explore, you got to remain curious. So that's all I'm trying to emphasize here, and really remain curious about even ways to improve automating these pipelines. Well, now we get to the fun part, the sexy part, and we really want to do some predictive modeling if needed. After we've done great data visualization and we look at where we might be able to help our businesses, we start looking at models. And I think everyone here would agree. If you don't, I would try to persuade you. Always try a lot of different models for your data set. And as your data set grows or changes over time, you really want to revisit which model works best. It's kind of sad that we're currently at a point where we're doing GPT-3 and reinforced learning and doing amazing things with all those things, but in our basic machine learning, supervised classification and regression, we really can't know ahead of time for a given sample of data which of these or which model is going to work the best. So it's really handy to write your code so it's easy to bring in a set of different models and run metrics on them. You're basically trying to have models that do, or excuse me, metrics that can tell you how well it's generalizing, that grades highly for good parsimony. And I think from what I've experienced, this can even be automated too, even the choice is what I mean. And just at a high level, we're just talking about machine learning tonight. I think that this pipeline, mind map, would need to be modified a bit for unsupervised learning, but I think it could be pretty close. And then of course there's reinforced learning on a higher level or a whole nother branch. And my favorite way to train that data is to split it with KFold cross-validation. The reason I love that is because I can test for generality very well, putting metrics in place to see how consistently it behaves. In other words, you don't necessarily want the most accurate model in any fold, but what you do want is the lowest variance in accuracy among folds. But not just that, but a balance of metrics that tells the story of good generalization and adequate accuracy. Because when the real data, the next set of data comes in that's a little different from your initial sample set, in my experience, it usually ain't going to be as good. And then finally, human oversight or Overwatch. Again, data science management needed, review, improve. But in my experience, if you start a good, healthy, supervised learning pipeline, you can automate it over time, even with the hyperparameters. And if you guys would ever like to talk about how that can be done with the hyperparameters in a very economic way, given the clock time, I'd love to do that as a side conversation on LinkedIn. And by the way, just a thought, the 10 of us could even start a LinkedIn chat group if we wanted, just a thought. And I'm really honored I got to speak to y'all tonight. Hopefully, if you've not seen something like this before, it looks completely clear. And here's that histograms part I left out at the beginning. And I can take questions if y'all have them, and thanks. I think I'll go back to this slide though.
I have a question. You were kind of alluding to stepwise selection. Was that true?
You know, I feel more like I go where the wind takes me on the data set in that case. But Sarah, I do suspect that there probably is an overall best process order that helps us get to easier, to an automated state easier. But Sarah, where I really struggle is if you really want to just automate it, would it be better to go on ahead and throw in, and I could accept this, by the way, why don't I just go on ahead and throw in a massive amount of engineered features before I do any reduction, and then I start stepping through a lot of these processes. And at that point, I think if I understand what you mean by stepwise, I would first reduce by collinearity. I would also reduce by correlation, just using linear or logistic regression. And I would go through all of these things in that way. But again, we're not even employing the labels yet when we do this reduction, I should point out. Oh, that's not completely true. When we're looking for correlation, we are looking stepwise to the labels, but I hope that answered the question. That's a bit tough, I think, without going through a literal example.
It did answer my question.
Excellent. I get a lot of questions around the PCA because people aren't familiar with it, but depending on your background, the reason I fell in love with PCA is because of my control system design background, and this is eigenvectors and eigenvalues, which are awesome. And so if you're looking at, and you can use PCA in more ways than just this, but for that collinearity, once you identify the variable, the features that are collinear, You just pick the one that's got the biggest eigenvalue.
Well, isn't each dimension of a PCA supposed to describe as much variation as possible?
Yeah.
So like the first eigenvector is a recombination of all of your features in a new linear model, if you will. And so I'm
Yeah.
sure I'm sorry.
Oh, no, please go ahead.
So, but there are other types of things very similar to PCA, like MSA or something like that. And there's a bunch of different flavors if you don't like PCA.
Yes. And, you know, this is what I usually do. I'm not saying this is all that you could do. In fact, you can tell I didn't even get into a hyperparameter discussion, but I would like to add hyperparameters to this if it were a longer discussion. But I liked what you said, Sarah, and the nice thing about our scikit-learn modules, when you apply the PCA from those, it already goes in ahead and orders them for you. So I really like that. By the way, PCA can also be used to figure out what features you could just drop because the variance to the label is just so low, you might as well just get rid of it.
That's true. You can use it as a way to drop features.
Any other questions? I hope this was helpful. You know, if you guys are really, what I found is even really experienced people have come up to me and just said, you know, I've never really thought to put that in kind of a combined thing, and it'd really be open to y'all's feedback. When we give this in a longer form, I'm wondering if it wouldn't be better to do this in more of a, to really draw a pipe and label the different steps in that format. But a lot of people can relate to mind maps too. That's why we did it this way first.
Well, very good job. Thank you for sharing with us.